Hi, my name is Isabella, and I'm talking about the importance of bond order today. So for one, what exactly is bond order? Well, bond order is defined as half the difference between the number of bonding and antibonding electrons. It helps us to know the stability of the bond between the atoms. Higher the bond order, higher the stability. It also describes about the bond strength. The higher the bond order, more will be required for the energy to break that bond. And I include this little picture that has nothing to do with it, but it was funny and, chemistry. Okay, next. We're talking about the finding of Linus Pauling. He is probably a name that most of us don't know. I didn't know until I did the project. But he was probably best known for working out the nature of chemical bonds, yet he also discovered, among many other accomplishments, the cause of sickle cell anemia, developed an accurate oxygen meter for submarines, and helped create synthetic plasma and determine the structure of proteins. So he was just a really smart guy. He was an American chemist, biochemist, chemical engineer, peace activist, author, and educator. But he's best known for working out the nature of chemical bonds. More fun facts about him: he was the founder of the fields of quantum chemistry and molecular biology. He was awarded the Nobel Peace Prize in Chemistry in 1954, and 1962 he received the Peace Prize. He is the only person to receive 2 unshared Nobel Prizes. On top of it, he wrote The Nature of the Chemical Bond, which is one of his famous published papers, and he was born on February 28th, 1901 in Portland, Oregon. On to the next thing. This title is Antiheroes, anti-bonding. So just like what I showed on the slide, placing an electron in the bonding orbital stabilizes the molecule because it is in between the 2 nuclei. Conversely, placing electrons into the anti-bonding orbitals will decrease the stability of the molecule. Electrons will fill according to the energy levels of the orbitals. These antibonds help with the bond order and the length. Electrons that spend most of their time between the nuclei of 2 atoms are placed into the bonding orbitals, and electrons that spend most of their time outside of the nuclei of 2 bonds are placed into anti-bonding orbitals. This is because there's an increase in electron density between the nuclei and the bonding orbitals, and a decrease in electron density between anti-bonding orbitals. So, also placing an electron in the bonding orbital stabilizes the molecule because it is in between the 2 nuclei. Electrons will fill according to their energy levels of the orbitals no matter what. They will first fill the lower energy orbitals, and then they will fill the higher orbitals. And that's something that we might not realize we're talking about bond order, but we have learned in even our high school chemistry class. And then if a bond order of 0 is obtained, that means that the molecule is too unstable, so it will not exist. And then I added a little picture just about them getting mad at an antibody because it reminded me of anti-bonding. So on to the next one. This one I labeled peas in a pod. Just from what it says on the slide, bond order determines the stability of each bond, just like we recently talked about. We use bond orders to predict the stability of molecules. If the bond order for a molecule is equal to 0, the molecule is unstable. A bond order of greater than 0 suggests a stable molecule. The higher the bond order is, the more stable the bond. This would also bring us into lone pairs. So I've said peas in a pod because they need to be pairs. But lone pairs, state of hybridization isn't influenced by the bond order of atoms. So that's good. And no matter single, double, triple bond, or lone pair, it's counted as one electron density region. For example, just to show bond order, is 2 bonds are formed between oxygen atoms, so the bond order is 2. It's basically just saying that this is how many atoms are involved, and this is their bond order. For the conclusion of this, I just put bond order is vital in the stability of bonds, and this does affect any molecule that we are aware of or is used in anything. We can see weak and strong bonds from bond order, and then bond order plays a crucial role in the formation of molecules. And then in the corner, I put a picture just to show how we figure out how stable a bond is, what the bond order is. You can see that's the number of electrons in the bonding element, number of electrons in the antibonding, divided by 2, and then you solve it. And the bond order is 3, and so it's a stable molecule because it is a bond order greater than 0. So that is my slide on the importance of bond order and how it affects anything, or just how it plays its role. So,
Thank you.
and here's my references.